Hello everyone, today I will present our work Remembering Across Blocks, Topology Conditioned Block Progressive Memory for Skeleton-Based Action Recognition. I will briefly introduce the task, motivation, and contribution, then our proposed memory framework, experiments, and conclusion. First, let me briefly introduce skeleton-based human action recognition. Skeleton-based human action recognition recognize human actions from sequences of joint coordinates. Because skeletons are compact and privacy-friendly, they are widely used in applications such as robotics, surveillance, and VR/AR. As shown in here, an RGB sequence can be converted into skeleton coordinates using pose estimation. Since pose estimation itself is outside the scope of our task, we assume that the skeleton coordinates are already extracted. Our model then classifies the entire skeleton sequence into an action category. In this work, we focus on offline action recognition, where a complete action sequence is given as input and classified into a single action category. I'll briefly introduce GCNs. This figure shows a general GCN architecture. GCN exploits skeletal topology as an inductive bias and aggregate information between connected joints through message passing. However, capturing long-range dependencies can be relatively difficult. In a GCN, skeleton joints are represented as nodes, and their relationship are represented by an adjacency matrix. Graph convolutions aggregates features from edges, which corresponds to one-hop message passing. To capture distant dependencies, GCNs stack multiple blocks. However, repeated aggregation causes two problems: oversmoothing and a progressive loss of fine-grained cues from early blocks. Our key motivation is simple. Instead of letting useful early block information disappear, can we progressively remember it across GCN blocks? We propose a topology conditioned block progressive memory that preserves complementary blockwise information, mitigates oversmoothing, and shapes better backbone representation during training. Next, I will explain how our block progressive memory works. At each GCN block, the learned topology A is used as a query to read the memory and predict the current representation H. The memory is then updated according to how well the previous memory explains the current block. Our memory consists of two matrices, M key and M bell, which together provide a nonlinear topology conditioned read operation. As shown in the figure, this is the memory state. Because each block feature is generated according to each topology, we use the topology as the query and read the previous memory to reconstruct the current block feature. As shown in the figure, this is the read operation. The reconstruction error measures the surprise information in the current block that cannot be explained by previous memory. A larger surprise produces a stronger memory update. We additionally use forgetting, decay, and momentum factors to stabilize this blockwise update. After the final block, we read the accumulated memory once more and adaptively fuse it with the final GCN representation using a gating mechanism. As shown in the figure, this is the gate fusion. Now I will briefly present our experimental results. We evaluate on 3 large benchmarks, NTU series, and kinetic skeleton from in the wild YouTube videos. For multi-stream evaluation, we train separate models for different skeleton modalities and fuse their prediction scores. Our method achieves strong performance across 2, 4, and 6 stream settings. We also evaluate individual joint motion, and bone motion modalities. The consistent improvements show that our memory is effective across different skeleton representations. As shown in the left figure, the baseline generally produces larger gradients in the later blocks close to the classifier, regardless of the training epochs. In contrast, our memory shifts from more gradient toward early blocks and middle blocks, encouraging them to learn more meaningful features. As shown in the right figure, the gain from memory are larger early in training and gradually decrease after convergence, suggesting that the backbone progressively internalizes the representations guided by memory. Quantitative, our method maintains higher interjoint feature variance and higher block-wise sensitivity entropy, indicating more diverse joint representations and more balanced block contributions. The qualitative results show the same trend. Compared with the baseline, our feature exhibit lower homogenization and clearer differences between individual joint representation. Finally, let me summarize our work. We proposed a topology condition block progressive memory to mitigate representation degradation in skeleton G-SHANs. The memory preserves complementary block-wise queues and improves the backbone even when memory is removed at inference. Our method achieves state-of-the-art performance across diverse 2D and 3D skeleton benchmarks.